As there are more satellites launched, the space around Earth is getting more and more crowded. And what this means is that there are these potential collisions between satellites where two satellites have to figure out whether or not they're on a potential collision course. And then as the time gets closer, you have to decide what you're going to do. And these decisions are happening more and more often. And of course, as we add giant constellations into orbit, then these decisions are just going to get exponentially more complicated. And so what are the nitty-gritty details of how this works? How is the data gathered? What are the ways that these satellites are being observed? And then what is the decision-making process to be able to decide what to do? And what role does autonomy play in the future of space exploration? My guest today is Dr. Sydney Dolan. They're a postdoctoral research associate and a member of the chair of systems at the Technical University of Munich. And we talk about Sydney's work in autonomous spacecraft debris avoidance and how various ground-based stations and even potentially space-based solutions can track the positions of debris, how satellite operators have to make these very difficult decisions and with a lot of unknowns to be able to try to minimize the risk of impact, knowing that if you mess this up, then you're going to increase the amount of debris and the decision gets harder down the road. So if you're interested in exactly how satellite debris avoidance works, enjoy this conversation with Dr. Sydney Dolan. Sydney, give me a sense of like what happens when two spacecraft realize that they might be on a collision course with one another?
Yeah, so great question. So for two spacecraft to know that a collision is coming, typically they're getting some sort of notification or what's called a conjunction decision notification, which essentially provides some information about when this will happen, the amount of covariance around each satellite, which is like the uncertainty around the satellite's location. So the time, the distance that they'll pass, the uncertainty surrounding it, and then the specific satellite IDs. And so these sort of screening processes that look for these collisions are doing this 24/7, and you can expect to get as much as like 7 days heads up about a collision. So the amount of heads up really dictates your response. If you have a 7-day heads up, these collision notification services typically operate on 8-hour intervals. So from 7 days out and every 8 hours forward, you'll probably get another update whether or not there's still that predicted collision. So if you're in that position, very likely you'll just probably wait it out and see if this notification will keep coming in, because the propagation models from 7 days out are very unrealistic, and it's nicer to wait. Around the 3-day mark is when you start to prepare a little bit more. So if you were to receive your first notification then, depending on some of the characteristics of the conjunction, you would either kind of put it in a pile of this is something I'm tracking as a concern, or you would immediately like kind of put it in this like discard pile, continue to wait it out. And then depending on your spacecraft's abilities, the 24-hour mark is typically like the do or die for a lot of systems. So 24 hours, we really do have a good sense of what the probability of collision will be like at the time it's likely to happen. And so at the 24-hour mark for most constellations that exist right at that point, they'll say if it's a 1 in 10,000 chance for SpaceX or a 1 in 1,000 chance for pretty much everyone else, that's the industry standard, you'll make a maneuver. And so the mechanics of these maneuvers has largely been a solved problem. What essentially you're going to do is take a burn in the in-track direction, and that essentially just scoots you a little faster in the potential trajectory and kind of resolves the matter. But it's this kind of like waiting piece and the determination of the notification. And then if you're not, one of these huge constellation operators, the maneuvering, well, the type of maneuver you should do is kind of solved the individual of like how much fuel you have and if there's any kind of opportunity to incorporate that with other mission planning of your spacecraft. That's very spacecraft specific.
And is this cool? Like, I know that there are ground-based tracking systems. I mean, there's NORAD, but I think there's like Leo Labs. There's a bunch of these groups that are doing all of this tracking. Are these notifications coming from one central entity, or is it like every satellite provider has their tracking supplier that they're keeping track of. And I use the word track too many times, but you know what I'm saying.
Yeah, you're totally fine. So the free service available to everyone, and this might have changed quite recently, but it used to be the 19th Space Force, like Space Force Defense Squadron. And they have a bunch of radars across the globe, and they would offer these notifications out to anything that's a public entity satellite. So they can't scan military satellites and warn them, but they can scan everybody else. Beyond that, you can purchase these services from Leo Labs. So there's a whole growing commercial industry where the Space Force will be sending out these notifications every 8 hours. But if you really were like, I want a notification just for me, I'll give you my ephemerides. So I'll give you my much higher fidelity trajectory information. And with this information, you can give me much better estimates of that collision. So there's a growing industry to really kind of support and provide better fidelity information that's more specific to the user, but it's about whether or not that specific kind of spacecraft company really has the money and kind of desire in purchasing.
Right. And like that was sort of leading to my next question. And I think you sort of half answered it there, but that you've got this, like you've got, say, ground-based tracking system that's sort of the catch-all that they're notifying, or like they're announcing that these two satellites might be on a collision course, but they're doing that based on their tracking of the position of the satellite. And what you're saying is that the satellite operators themselves, they're maintaining far more realistic information about their existing orbits, and then they're supplying this data. So is that going to just these private companies, and are they like selling their data? I'm trying to understand how the data flow works, that you can then both provide to it, but then also come back from it and so on.
Yeah. So most companies now will provide their their ephemerides, that high quality trajectory, to the Space Force, like a commercial company. So then with this updated trajectory, the Space Force will then run future collision checks with that trajectory, and they can give you better estimates. But if you're also to purchase a service like Leo Labs, you can share it with them as well. So I think it's really there's also, like, if we're thinking, constellations are largely the kind of biggest populace in orbit right now. So these are very, very capable satellites that have very high quality recognition of where they are on board. So that ephemerity in that case is very, very useful and is going to help with the collision resolution process. I currently work on a university CubeSat. We are not going to have that sort of high quality ephemerity available. So there's also kind of this underlying current of different qualities of trajectory knowledge for different satellites, and that aspect to model as well.
But there's no regulation, like you're not required to provide this information.
No, it's all opt-in.
Right. Okay, so then how, like, if you're a satellite operator, and obviously it depends on how many satellites you're watching, how often are you watching these potential close calls come in?
So if you have a fleet of satellites, it really is like a 24/7 job. So I have a few friends that used to do like spacecraft collision operations very early days at SpaceX, and it really was like night shifts as well to resolve these, because I think this is one of the really clear differentiators between space traffic and air traffic management, is that serious events in air traffic, we can resolve the airspace and really stop planes from being in an area. But serious events in space, there's no way to stop physics. And so the ground support to really support large constellations of satellites is a 24/7 business. I think, what was the number? In 2023, they were sending out 600,000 of these collision avoidance notifications every day. So that's to everybody across the globe, but 600,000 specific collision events to think about. And yes, a huge portion are kind of easy throwaways, but that's really kind of indicative of the scale we're dealing with now. When we're with the space industry growing, it's going to be, bigger and bigger of an issue.
And it feels to me like, like a lot of people are worried about the Kessler syndrome. They're worried about these satellites crashing into other satellites and creating this sphere of metal around planet Earth. It's like a buzzsaw. If you try to fly through, you'll be ground down to powder. And it feels like the real risk in the short term is that these satellites are being forced to use a lot more of their propellant to just stop crashing into each other.
I think it's multiple things. I think because the largest populace in orbit is constellation operators, and these constellations have electric propulsion, I don't think for those specific companies the propulsion usage is something that's like a significant constraint at this point, or it's quite difficult to model without their cooperation a little bit. I think largely kind of the bigger issues, what I would say in the field are now, is the way to quantify risk meaningfully as these systems continue to grow. Because as I suggested with that 600,000 number, there's really a lot of opportunity for these huge collisions. But because of the ways we're thinking about risk now, it's just like very... How am I trying to stay here? The way we model risk makes it very, very challenging to like really realistically say the danger that exists right now. And so space is big enough that we can kind of get away with a lot. And the people that are being burdened have the EP, but I ran away on this point. I apologize.
No, that's fine. It's fine. But right. I mean, I think that idea, I had read recently that right now, with the amount of satellites that are being added to these various constellations at various orbital levels, and all of the affiliated boosters and fairings and defunct satellites and all of that it's not sustainable, right? We just can't keep this up. That at some point, the collisions get more common, the near misses get more common, and the cost of all of this, another tragedy of the commons situation. How far along that sort of curve do you think we're at right now?
Yeah, I think that's really what's so challenging to know, because our ability to model the debris out there and kind of the debris evolution is really quite limited. So Kessler syndrome, this phenomenon of essentially rendering a whole orbit unusable, our ability to actually model how satellites like explode in space is like so limited. And so what we're doing now for past collisions is we just kind of assume a set amount of debris out there exists and it's undetectable, and that's just an assumed risk. And that's not really, if we're talking about an orbit that's so polluted that we can't use it, we really would need to understand the pollution that exists now, and we can actually do that. And then if we were to actually think about, the damage of future collisions, our ability to model these collisions right now, I would say, is very, very remedial and an open area of research to really kind of think about these hypervelocity collisions and where exactly things kind of explode and which orbits they go into.
Yeah, I know, like when we saw a couple of anti-satellite tests, we saw debris going quite high off of the orbit that it was originally on, and even risking potentially the International Space Station. But in the regular world, you just want to do more tests, see what happens. Destroy 1,000 satellites in orbit to see how well that all works out.
Yeah, that would give us a good model, but would not be good for the world.
Yeah, exactly. It would give us a very good model, but a very bad space environment. And so you have to. So how do you get better at this? Is it simulations?
I think some of it has to be improvement of the sensing technologies itself. Essentially, like we kind of back end. The way these collision propagation models are done now is that we're learning a lot from that Iridium collision several years back. Of this was the populace that was created, and this is how we've measured it over time, and then trying to kind of fit, the debris trajectories off of that based off of the two satellite geometries when it occurred. But the ability to sense debris smaller than a centimeter is also incredibly important, and our ability to really understand where those debris are as a result of that collision, because that collision occurred high enough that there's still a fairly decent chance that there's a lot of debris somewhere around there, but we don't know. And that kind of goes back to that like just haphazard rule of thumb of like, we're assuming this much debris is sort of out there, but we can't really see it at any meaningful capacity. So for these models to really advance, I think the physical sensing has to step forward to support them.
And is that a ground-based solution, or do you think there are space-based solutions that would be very productive?
I would like it to be a mix of both. Like I work a little bit on this like space-based sensing side, so you're asking a biased source perhaps, but that's
fine. That's fine. You can be as biased as you need to be.
The value of space-based sensing methods is that you don't have atmospheric interference, so the sort of noise that you would maybe expect with seeing something from the ground isn't there. So that's some of the interest with why you would want something in space, and also that it would just physically be a lot closer, so perhaps you could see things. But yeah, I think there's a lot of interesting work being done to kind of look into how we can study these very, very small objects. Yeah.
What would that look like? I mean, like a radar system in space, a constellation of radar systems? What would be sort of the best, highly biased, space-based detection system, do you think?
So this is where I'll plug my work, but also I'll plug kind of what a future system would look like. So I currently work with a specialized type of camera called an event camera. So conventional cameras are captioning this wonderful interview, but event cameras are a different type of camera that tracks motion only, and it updates on a pixel by pixel basis. So it gives us an ability to see things at a much finer spatial temporal resolution, which is good for fast objects in space. And it also allows us to see really like speedy and bright things, which is good when we're thinking about like really tiny objects to look for in space. So when we're thinking about sensor development more broadly for in-space observation for debris, we need something that's able to see very, very dim objects, and then that you would, so very, very dim, fast-moving objects, which is kind of what motivates the project I'm on. And then you would also want this sensor you would really need like quite a significant fleet of satellites around orbit. So you would really want this to be something that's not JWST sized. There's kind of this whole element of kind of like the manufacturing of it and the standardization of it for it really to be put on a lot of spacecraft. So there's been some work as well on how to repurpose star trackers and see if you can get, useful, maybe not 1 centimeter, but maybe 1 to 10 centimeters. So we can just kind of raise the level of awareness in the space environment as well. So I'm not an optics background by trade. I'm sure there's other kind of optics theory we could pull from to inspire kind of the development of sensors in this area as well.
But I'm sure, like at this point, I know my audience, and they're thinking, can't we just install this hardware onto the existing constellations of satellites that are out there right now? Is this an Arecibo? I mean, you said not James Webb, but it is a fairly large dedicated thing with its own ability to either do low light imaging, maybe an infrared or something. Or is it something that you could just kind of bolt onto the side of an existing satellite to give it some more situational awareness and also participate in a larger network?
So just to clarify the question, is this about the system I work on, or what a system would need to look like for this?
Extending what you're working on, like you're working on a CubeSat, right?
Yeah.
Right. So, I don't know how many U's is your CubeSat.
It's 6U, it's tiny. Yeah.
Right. And so you're testing out your ability to detect moving debris in range of your right. And so give me a sense of how much range, what do you think you'll be able to detect with this CubeSat?
Yeah, so the current experimental characterization of this sensor has shown that I can see apparent visual magnitude of around 14. So the human eye on the AVM scale maxes out at seeing objects that are 6. The sun is negative 26. So to give you a sense of the scale, log, lower positive number means dimmer. And so, at least the sensors are better than our eye. That's always kind of a promising indicator. But we're hoping that we'll be able to see fairly dim objects. We're trying to target for this CubeSat mission, rocket bodies. I think where we're thinking of in sun synchronous orbit will be a really good opportunity to study what's a more detectable piece of debris, but not necessarily a bright piece of debris, and then step forward with the technology from there.
Right. And so then if you could miniaturize this technology and then have this be piggybacking on some existing, if an entire constellation of communication satellites, could they all have one of these installed on board that is then contributing to a mesh network of detection?
Yeah, that would be super ideal. And I forgot to plug their other benefit is that because of this like pixel by pixel update, the power consumption is way, way lower than a conventional camera. So that's like quite advantageous for just sneaking it on to a satellite as well.
Right. But I mean, you're looking at potentially tens or hundreds of grams, not thousands of kilograms.
Yes.
Right. So then give me a sense of how you think about, I mean, I think most people think about just space, right? There's like Earth, there's the atmosphere, and then there's space, and there's orbit.
Right.
But how do you think about sort of altitude and sort of in context with the work that you're doing?
I have no idea about this question. I'm so sorry.
Well, okay, so I'll give you sort of my answer to this, and sort of maybe that's a jumping off point. So, like for me, low Earth orbit, what you have is you have this friction with the atmosphere. You have this process that is trying to bring satellites back down to the Earth, and so mistakes can be cleaned up.
Yeah.
The place is sort of self-cleaning. Mm-hmm. But then, as you get higher, you get wider fields of view. You can operate with less satellites, and you're in more space. You have more room to breathe.
Right.
But also, any debris that you create is there for a much longer period of time. It could be decades. It could be potentially centuries when you hit. And I wonder sort of how as we start to think about this common resource, how we put those priorities onto those different orbits.
Yeah. So I mean, I think some of the work that's looking into kind of space traffic management more broadly is kind of looking at this idea of orbital shells and how we can really kind of like create proverbial like traffic lanes or parking spots for different satellites. And then kind of related to that, a lot of this orbital shell work is actually looking more at geosynchronous orbit, which is very advantageous for telecommunications, and how we can really kind of reserve spots for countries or communities that haven't really built up their space program yet, because access to space can really, I mean, it obviously incredible, but it's a really precious resource that everybody should really have equal access to. And so how we can kind of think about making sure that the access we have now is something that if other countries wanted to build a CubeSat, that they actually have the means to, that there's room for them to really build out their own program as well, is kind of another way to look at this problem, I would say.
And then, I mean, is anyone thinking about like the future of lunar orbits, the complexity there?
The lunar
Mars
traffic?
Orbits? Yeah.
I would say this is definitely like the corner of my knowledge too much. I don't look too much in the cislunar domain. I would say it's very, very militarized. So I haven't had the chance too much to really look into like the constellation design there, the approach. I feel like it would need to be quite different from like low Earth orbit, which is, commercial operators, a lot of telecommunications companies, a lot of internet companies. The moon, I'm not so sure how much those sort of entrants will be there, and those sort of people will really get to dictate the cultural norms.
But I wonder, the farther away that you get from Earth, the longer the communication times become. And so this is where I think your work in autonomy becomes more and more important. I mean, if you've got a bunch of satellites that are orbiting around the moon, you've got a 1.3 second time to reach the moon, the same to come back. 24 hours warning. Yeah, you can absolutely still deal with it. But what if decisions have to be made very quickly? Do you see more autonomy in spaceflight as we move farther and farther away from the Earth?
Yes, I think this is definitely like a super important area for autonomy to step into. I think what we say when we're saying autonomy is that we want to build some sort of robotic or learned system that is replicating kind of the human decision making we would expect if a person was there doing the same thing. And so I think a lot of the work that comes when you're moving further away from the Earth and further and trying to branch out into these scenarios, it really requires a deep understanding of kind of the human decision making that would occur in those equivalent scenarios. So I think part of the work honestly involves a lot of really kind of like tailored characterization of ground station operations, and also working with like scientists as well and technical scientists, and really helping them kind of step through these decision trees of, what looks interesting to you, how can a spacecraft respond if it was supposed to see said interesting thing, like really building out the mental model for a human and then seeking to replicate that on a spacecraft.
Yeah. And I think, we were talking sort of before the interview about like how Perseverance helped choose its landing site. That I think one of the problems we saw with Ingenuity was that it made a bunch of flights, but eventually it was starting to fly in places that were actually a little dangerous. It couldn't quite make out its terrain below. It landed at a bit of an angle, hard, broke its rotors. So when you're on Mars and communication can be 20 minutes each way, if you want to be productive, you need that autonomy. But at the same time, how do you train something that's novel, that's new? You don't know what you're looking for in terms of science.
Yeah. It's quite obviously like a challenging and open area of research. I think so. Part of it is that it's very interesting, the spacecraft operations process of really breaking down into mission phases and initiating those phases. This is the level of autonomy that we kind of expect to see on Mars rovers, of these day-to-day schedules get uploaded to whatever rovers are on Mars, and then they just kind of initiate and follow these schedules along. So the next level of autonomy that would be super ideal, that is still kind of quite a difficult planetary science problem as well, is like, how do we kind of let them creatively explore? And as you said, like, this is the Ingenuity helicopter was a system that was weighing the like scientific value at the cost of kind of its engineering ability. So this sort of trade-off on, so like I work with a lot of scientists, like the passion to really explore these planets is quite infectious, but then you're also on the engineering side and you're trying to be like, how do we weigh these two things? It's quite challenging. I think part of the work I said is I think it comes back to kind of like fundamental systems engineering principles of really looking at, the objectives that you're thinking of more broadly that are kind of defining the operations themselves, and also the engineering abilities and the sort of lifetime that you're expecting. Like, I think some of the inherent design of the helicopter on Mars kind of maybe led to more aggressive scientific pursuit that you probably would not find that same sort of engineering science balance in other missions.
But when you think even farther, you think about, say, the upcoming Titan Dragonfly, which is going to be out at Saturn, and that is even farther away. And you can't micromanage that helicopter that is flying around in the atmosphere of Titan. Like, it's got to be able to take off, land, deal with hazards, because you're not going to have time to get in there and really manage it. But at the same time, you can imagine the scientists like, the helicopter just spent the whole day looking at a rock. Right. And that's not what we wanted. Right.
I mean, if you talk to them, they'd still probably be very happy.
Maybe that's what they want. Yeah. All right, fine. The helicopter spent the day flying around having fun.
Yeah.
Right. And so you need to be able to, say if you're going to do machine learning, you need to be able to iterate on the things that it's doing in an alien environment. So you don't have the reinforcement yet.
Right.
How do you think about those kinds of problems where the data is sparse and your ability to reinforce is slow?
Yeah. So I think this is where kind of like techniques from machine learning and kind of online learning come into improving the autonomy of these systems. So in these techniques, you would really kind of be instead of knowing the science that's out there, so you can't say we're going to look for, like a surface ocean. We can't guarantee those sort of things. You would instead really be training systems that learn to identify quality data well. So there's a lot of autonomy work now that's looking at, we have these huge constellations around the Earth, but I think I read one paper that said 93% of the time, these Earth observation constellations can't see Scotland because of clouds. So if you really want to see the crown of Scotland, you're just out of luck. So the ability to really build these systems that can identify what is a good photo, for example, is quite important. Of how can we down select the photos? We only have a select amount of bandwidth to really relate that to Earth. So while we might not always necessarily know what we're seeing, we still know what quality and useful data is, or maybe not even quality, but what could be more priority for the scientists at the moment, because it's probably all very useful in different forms. So that could be a lot. That's where I view a lot of the kind of value of autonomy in these more far off regions.
Yeah. And then take that to its sort of ultimate idea is sending a spacecraft off to another star system.
Yeah.
Where you're now taking years to hear, how's it going? 8 years later, fine.
Yeah,
right?
I mean, that one would be really just such a complex problem where you would need multi-step reasoning if you're really letting something, if you really only have a few messages it could send back. You would really want to be building something that's can kind of not just discover something, but then reason about the next stages of discovery. Because I think a lot of the assets we have now really focus more on the discovery piece, where to look and really how to cultivate what they've looked at, and not, if this is true, then what's the next step? That's usually where people kind of fill in the blanks.
So, when do we get von Neumann probes?
Yeah, I don't know. I can't say now. If I had all these answers, I would be a NASA admin or something.
Yeah. I mean, it's such a fascinating concept. I just sort of think about when you bring together our ability to 3D print, manufacture stuff, when our ability to start to autonomously navigate around the solar system, our ability to harvest material and be able to, potentially make copies of themselves, that gets crazy. And it feels like that's the inevitable path that our curve is on, but maybe it's a couple hundred years from now. And
yeah, probably a very minimum.
yeah, for sure. Sydney, what are you obsessed with right now?
Yeah, I mean, I think one of the things that I've been obsessed with recently, I work in Munich in Germany, and so the German Space Operations Center is nearby, and so I get to kind of learn a lot more about the German approach to spacecraft design and spacecraft operations, and some of the work they've been doing here has been really looking at characterizing human operator response to different possible collisions. And so some recent studies have found that when you look at some of these more tricky collisions that are kind of these corner cases where you're deciding, do I really want to move? Is this warranted enough? If you give it to the same set of 30 spacecraft operators, there's only about 50% agreement in their decision making, which is really, really not good. What one person is saying we need to move for, another person is saying, I'm gonna. So this, if that was aircraft, we would be really stressed to hear that information. So I think this idea of how we model, risk in this setting, as I said, spacecraft risk is a 1 in 1,000 risk is really, really serious. But as a human being, if I'm thinking 1 in 1,000, the human brain really cannot wrap your mind around a 1 in 1,000 chance. That's just not something I think is physically possible. So how we can really understand operator response to collision avoidance, and how we can kind of really build intuitive systems when we're kind of really working in what is a high consequence but relatively low risk space, I think is a very interesting open problem with hopefully a lot more research to come.
But I mean, it gets right at the heart of just humans inability to conceptualize risk.
Yes.
That we hop in our cars, but we're worried about sharks.
Yes.
And so you can see that risk issue. So, I mean, is it that we give people a better understanding of risk, or do we have systems and policies that guide their decision-making process? It's kind of nice to have people operating a bit by their gut because they can make decisions quickly. But
right.
if your gut really is bad at risk, do we just teach them all to play poker?
Yeah, I mean, it's quite, I think ideally we want all of them to make the same decision. We don't want it to be variable based off of who's showing up on Tuesday. So like at the bare minimum, there needs to be some policy they all need to follow. But I think it's very interesting, these like corner cases and what one determines as significant or not. I think honestly, if we're looking at like 100-year predictions, I think we'll look back at how we're doing collision avoidance probability now and be like, that was ridiculous and not the way. I think the way we're doing it is the best we can with what we have. I can't suggest an alternative, but I can say, hey, there's just no way it's going to be like this in hopefully like 30 years.
Do we just hand it over to the computers?
No, it comes down to like the fundamental mechanics of the equation itself. We're like taking the roughest approximation, like the most over approximation of where a spacecraft could be, and the biggest approximation of where the other spacecraft is. And then on top of that, like the biggest possible approximation of their like combined surface area. So you're just getting this like hugely bloated number for risk that sometimes pops out to be relatively low. So I think, with better sensing, we'll likely have like a new collision metric. Ideally, like 20 years or less, but who knows how long? Because just this 1 in 10,000 it's not possible to really even to tell a robot that. Actually it breaks a lot of the robotics because you're on like the log scale that doesn't
right.
do well.
It's just all edge cases. Robot doesn't know what to do with it. Yeah, that's exactly. Really interesting. Well, Cindy, thank you so much for taking the time to chat with me today, and good luck with your mission.
Yeah, thank you so much.
I hope you enjoyed the conversation with Dr. Sydney Dolan. We continued the conversation, as we do, with a bit of a bonus discussion about how people can get involved in engineering projects. I know that a lot of you that are watching this, you love space. You've got some kind of practical experience in either programming or some other science, but you'd like to be able to get involved in space exploration, in astronomy, and it feels like this giant gulf between where you are and being able to have any kind of understanding. And so Sydney and I talk about ways that people can get involved in various projects, interesting competitions that the various space agencies put on, and the kinds of hardware, software that you might want to become more familiar with to be able to gain that experience. So that conversation is available for free over on Patreon. You just have to follow us on Patreon. You can get access to that additional interview. Now, I'm going to give you some final thoughts, but first, I'd like to thank our patrons. A special thanks to Abe Kingston, Adam Schaefer, Andrew Gross, Barry Lake Roofing, David Gilton, and David Matz, Dustin Cable, Greg Feely, Hudson Moore, James Clark, Jeremy Mattern, Jim Burke, Jordan Young, Josh Schultz, Michael Purcell, Paul Rohrbach, Sean Sargent, SpiderSwap.io, Stephen Fowler-Melney, Thomas L. Skadron, and Vlad Shipley, who support us at the Master of the Universe level, and all our patrons. All your support means the universe to us. So in addition to astronomy, I'm very fascinated by spaceflight. And, as we have more and more satellites up there in orbit, we're going to have to figure out what to do. And we've seen this problem happen before, the tragedy of the commons. This is a common space, pardon the pun, that we have to learn to work with. And I've done a bunch of interviews about this. The one that you saw today with Sydney Dolan, but I've also done additional interviews about the rising problem of space junk, how we can deal with an overly congested orbit, and I will provide some links in the show notes below. All right, we'll see you next time.